If you've been following along with some of the examples, the truth tables that we've been doing whenever we've been talking about starting with the truth table and coming up with the sum of products expression, either by isolating the ones within the truth table or, more importantly, using a Karnaugh map in order to come up with the most simplified set of products for our sum of products expression. Well, some of you may be thinking, yeah, right, like we start with the truth table. Sure, yes, we do. In fact, let's just start with something really simple, something that we've already got a little bit of experience with. I don't know, how about, and let's see, here we go. There we go. All right, I've got a basic addition there. All right. 1 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus, good Lord, it looks like there's going to be a lot of zeros here. 1 plus 0 is 0, carry the 1. 1 plus 0 plus 0, 1 is 0, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. Here we go. 1 plus 1 is 1, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. And as a quick refresher, if we were doing this in 2's complement, this would be a perfectly valid 8-bit addition. But if we were doing it in unsigned binary, we'd have a carry into the 9th column, which means we would have had an overflow. Just a side note right there. But the electronics to do this, how does it work? Well, we usually will start out with a truth table. And let's just start with this least significant column right there. The least significant column, there's always just the addition of 2 bits. Just the bit from the first value, which I'm going to call this first row A, and then the second bit we're adding is from the second row. We're going to call this B. And so we're either adding 0 to 0 to get 0, 0 to 1 to get 1, 1 to 0 to get 1, or 1 to 1 to get 0 with a carry into the next column of 1. So actually there are 2 truth tables here. There's one column for the sum, I'm going to call this S, and there's one column for the carry, C. So what we've got here is just a 1-bit adder. All we're doing is we're adding 1 bit to another bit to get a sum and a possible carry into the next column. And so this truth table right here, which we created not necessarily by just making up a truth table, but because we're trying to solve a specific problem, there you go. Now, right off the bat, you should be able to, if you've been following along with these lessons, you should see that we've really got 2 very simple truth tables here. We've got one truth table right here, which is for S, the sum, and one truth table here, which is for C, the carry. Now, C, the carry, that's pretty easy. We just have a single 1, and then you know that anytime we're trying to create just one 1 in a row of the truth table, that's just a product of all the inputs for that truth table. So we've got when A is a 1 and when B is a 1, the carry is going to output a 1. All right, so, and in fact, that's exactly the case that we had here. The sum, however, is a slightly different truth table. In fact, if you're familiar with the exclusive OR, it looks like an exclusive OR, but let's actually do a real quick 2-input Karnaugh map. All right, so I'm going to make a Karnaugh map, and a 2-input Karnaugh map just has 4 cells. 2 rows for the A's, 2 columns for the B's. So A can be 0 or 1, B can be 0 or 1. And this cell right here is the 0, 0 cell. So 0, 0, the sum is 0. This cell right here is 0, 1, 0, 1, the sum is 1. This cell right here is 1, 0, 1, 0, the sum is 1. And this cell right here is 1, 1, the sum is 0. Now, there are 2 things that I wanted to get out of showing you that. The first thing I wanted you to get was, hey, there is such a thing as a 2-input Karnaugh map, right? Usually we don't need it because the simplification is pretty straightforward whenever it comes to simplifying things in just 2 columns. But the other thing I wanted to show you was that the 2-input Karnaugh map reveals this is not, we can't really simplify things very well whenever it comes to the exclusive OR. Remember, the exclusive OR in itself is not a gate. It is actually a sum of products expression. And that sum of products expression, we see we have a rectangle of size 1 and another rectangle of size 1. Two rectangles of size 1. And those two rectangles of size 1, well, because they're of size 1, no inputs drop out. All the inputs are present in all of the products. So this product right here is going to involve both A and B. What we want to do is output a 1 when A is a 1 and when B is a 0. So we put a bar over the B. This one right here also going to be a product of both A and B, except this time it's when A is a 0, so A gets a bar, and B is a 1. So the sum, that S expression, is going to be A bar B ORed with A B bar, which it turns out is, in fact, the expression for a two-input exclusive OR. And we figured that out from the Karnaugh map. Doesn't simplify any more than that. That's as simple as it gets. All right? So that takes care of what happens in this first column. And by the way, that first column is referred to, what we're going to do is we're going to have A and B, and then the output is going to be the sum and a carry into the next column. Now, this device right here is called a half adder. So that's a half adder. Well, you know, you think about it, it's actually a 2/3 adder. If you think about the full adder, which is what we're going to do next, adds 3 bits, but 2/3 adder just doesn't roll off the tongue, I guess, as well. So that's a half adder there. And what we're going to do next is we need to now come up with the circuit that will add A, B, and the C, the carry from the previous column, into a sum and a carry to the next column. So let's do the truth table for that now. All right, the truth table for the full adder, this guy right here, the full adder, that's going to have 3 columns, right? Because we have 3 inputs. So let's go ahead and make our 3 input truth table here with A added to B with a carry from a previous column. And now we need to also have 2 columns, 1 column for the sum and 1 column for the carry out. All right, so 0 plus 0 plus 0 is 0, no carry into the next column. 0 plus 0 plus 1 is 1, no carry into the next column. 0 plus 1 plus 0 is 1, no carry into the next column. 0 plus 1 plus 1, that's 0 with a carry into the next column. 1 plus 0 plus 0, that's 1 with no carry. 1 plus 0 plus 1, that's 0 with a carry into the next column. And in fact, I may be going through this kind of quick. Let me just go ahead and show you an example. 1 plus 0 plus 1. In other words, A is 1, B is 0, and there's a carry from the next column. The result is 0, and there's a carry into the next column. And then this column right here, we've got A and B are both equal to 1. I don't actually have that one here, but A and B are both equal to 1, and there's no carry from the previous column. That's equal to 0 with a carry out. And then in this case, we've got a column right here. A is 1, B is 1, and there's a carry from the previous column. That gives us a result of 1 with a carry into the next column. All right, so there is our truth table that defines the operation of the full adder, every possible consequence. Now, one thing that we can look at here is the fact that S, the output S, the sum, that's going to be a 1 for just 2 possible conditions. One condition where there's 1, 1 at all of the inputs. So 1 plus 0 plus 0, or 0 plus 1 plus 0, and so forth. There's going to be an output of 1. The only other time we're going to output 1 as the sum is if all 3 inputs are a 1. If all 3 inputs are a 1, we output a 1. Now let's look at the next column, the carry column. What the carry column says is that if I've got 2 or more 1s at the inputs, I'm going to have a carry. In other words, if I'm adding 0 plus 0 plus 0, there's not going to be a carry. If I'm adding 1 1 to 2 other zeros, there's not going to be a carry. If there's 2 1s at the inputs or 3 1s at the inputs, I've got a carry. All right. Now, let's go ahead and make the Karnaugh maps for these guys. So I have 2 Karnaugh maps. I'm going to make 1 Karnaugh map for each of the output columns. So I have to have a Karnaugh map for S, where I have A, B, and C as the inputs. Remember your gray code, that odd numbering, right? And 0 and 1 as the columns values for C. All right? Now, and then I also need to have a carry. All right, also having A, B, and C. And this is the carry out. I should probably specify or distinguish the carry in from the carry out. All right, 0, 0, 0, 1, 1, 1, 1, 0, and then 0 and 1. So if in this column right here, I have all 3 inputs are a 0, I have 0 with no carry. This column right here, I have 0 plus 0 plus 1, I have 1 with no carry. This column right here, I have 0 plus 1 plus 0, that's 1, no carry. This column right here, or excuse me, cell. Have I been saying column? Sorry about that. This cell right here, this is 0 plus 1 plus 1, that's 0 with a carry. This cell right here, 1 plus 1, this cell right here, 1 plus 1 plus 0 is 0 with a carry. This cell right here, 1 plus 1 plus 1, that's 1 with a carry. We see that right here. This cell right here, 1 plus 0 plus 1 plus 0 plus 0, 1, 0, 0, that's 1 with no carry. And this cell right here, 1, 0, 1, 1, 0, 1, that's 0 with a carry. All right. Now, sorry about doing that kind of quickly, but hopefully if you've gone through the past 4 episodes, you've seen this ability, you've got this ability down to be able to transfer the truth table to the Karnaugh map. And in fact, you might have seen that I didn't really even need the truth table because I was just doing all the addition and so forth. And I started out doing all the additions instead of doing a copying from the truth table to the Karnaugh map. So what we're going to do now is make ourselves a little bit of room, because remember, the Karnaugh map contains all the information that is in the truth table plus a little bit more. All right. So we're going to go ahead and get rid of this truth table so we have room in order to do our rectangles and products. Now, let's look up at this guy. This guy, I've got a 1 here. I can't, and remember, the goal is to make rectangles around the 1s, to group the 1s in rectangles that follow a few rules. One of the rules is that the size of every rectangle must be a power of 2. So we can have 1 cell in a rectangle, 2 cells, 4 cells, 8 cells, or 16 cells. Cells can overlap, but every single rectangles may overlap, but every single rectangle must have at least 1 cell that's unique to it. Rectangles can cross borders, but they can, but once again, adhering to the rule where you have to have a unique cell in every rectangle. We have to cover all the 1s in the rectangle with at least, we have to cover all the 1s in a Karnaugh map with at least 1 rectangle. And I'm sure I'm missing some rules, but let's go ahead and make some rectangles. So this one right here, I can't pair it with the one to the left, I can't pair it with the one below it, and I can't pair it with the one above it. It has to be all by itself. And in fact, same thing for this guy. I can't pair it with the one to the right, the one above it, or the one below it. Same thing for this guy. I can't pair it with the one next to it, above it, or below it. And this one also can't pair it with the one next to it, above it, or below it. Now, this may not look like a proof, but it is a proof of sorts. because what you see here is the fact that any sum of products expression for 3 variables is going to have at most 4 products, and at most 4 products that have all the inputs as part of each one of the products. Why do we know this? Well, each one of these cells is going to generate a product with exactly 3 inputs, because we didn't double the size of any rectangle, so no inputs are going to drop out. And there's going to be 4 of them. They're spaced out kind of in this checkerboard so that there's exactly 4 products that are going to result. What does that mean? If I moved any one of those moved any one of those ones that are surrounded by the rectangles, then, for example, if I move this one up here, then it would pair with both of those and this rectangle would disappear. I would lose a rectangle, lose a product, and 2 of the existing products, 2 of the leftover products, would actually lose a term because they were able to double in size. A simpler expression. I can't add a 1 anywhere here without simplifying. I'd still have 4 products, but they'd be at least simplified. So if I put a 1 here, for example, this rectangle could double to there, this rectangle could double to here, this rectangle could double there. All 3 of those rectangles, I would have 1 less input term, simplifying the expression. This shows us that the most complicated sum of products expression we're going to get is 4 products, each one having all 3 input terms. So let's go ahead and make this guy. This guy right here is going to have a product of A, B, and C. And in this case, it's going to have A as a 0, B as a 0, C as a 1. So bars over A and B. This guy right here is going to have a product A, B, and C. There's a 1 and a 1 for A and B and a 1 for C, so all 3 of them remain uninverted. This rectangle right here, A and B and C. A is a 1, B is a 0, C is a 0, so B and C get inverted. And then this product right here for this rectangle, A and B and C. A is inverted, B is not inverted, C is inverted. A is a 0, B is a 1, C is a 0. And so what that gives us is our sum is equal to A and B and C with A bar, B bar, right? Ored with A, B, C, this guy, ored with A, B, C, this guy with bars over B and C, ored with A bar, B, C bar. Let me try that again because I kind of skimmed over some things. So S, our sum, the circuit that is going to generate this pattern of 1s and 0s in the basement, right here, that guy right there, is going to be S is equal to A bar, B bar, C, or A, B, C, or A and B bar, C bar, or A bar, B, C bar. All right? Now, like I was saying before, when does the sum output a 1? It outputs a 1 for only 2 conditions. One condition where exactly 1 input is a 1, and the other condition where all 3 inputs are a 1. So this is the condition where just C is a 1, this is the condition where just A is a 1, and this is a condition where just B is a 1. There's the condition where all 3 are a 1. The expression makes sense. Let's take a look at this guy though, the carry. We do have a simpler expression here. In fact, if we take a look at this one, I can't pair it with the 1 next to it, I can't pair it with the 1 above it, but I can pair it with the 1 below it, and I can get a rectangle right there. This one right here, I can't pair it with the 1 above it, I can't pair it with the 1 below it, but I can pair it with the 1 next to it. And lastly, we've got this one right here, which can't be paired with the 1 to the left of it, can't be paired with the 1 above it, but it can be paired, well, below it, but it can be paired with the 1 above it. So I've got 3 rectangles, 3 groups, which are going to create 3 products for our sum of products expression. Let's start with this one right here. We've got values of A, B, and C. This cell right here has A, B, and C equal to 1, 1, and 0. This cell right here has A, B, and C equal to 1, 1, 1. We see that C is the one that changes, so it's the one that drops out, and we're left with the product A ANDed with B. Since both A and B are 1s, we don't need to have inverters over either A or B. Let's take a look at the next one. This guy right here has values for A, B, and C. The top cell is A is 1, B is 1, C is 1. And the bottom one is A is 1, B is 0, C is 1. 1, 0, 1. We can see B changes, so it drops out, and we're left with A is 1 and C is 1. That gives us a product A and C with no bars over anything. And then this guy right here for values of A, B, and C. What you're looking at are A, this top one is A is 0, B is 1, C is 1. And this cell right here is A is 1, B is 1, C is 1. And we see that A changes in this case. A drops out, we're left with the product B ANDed with C. Once again, none of them are inverted. So our expression for the carry out is equal to A and B, ORed with A and C, ORed with B and C. Does this make sense? Well, if we think about our discussion before we started making the Karnaugh maps, we said that the only time we have a carry out is if either we have 2 inputs that are 1, or if we have all 3 inputs that are a 1. Well, there are only 3 ways that only 2 inputs can be a 1. Either A is a 1 and B is a 1, or A is a 1 and C is a 1, or B is a 1 and C is a 1. What if all 3 of them are 1s? Well, all 3 of those products are 1, and our carry out is going to equal a 1, and we're going to get a carry into the next column. Now, one quick thing before we go. If you look at this full adder and half adder, so we've taken care of a circuit to do the least significant bit, the half adder, and we've taken care of a circuit for the full adder for the next bit. Do we need to create another circuit for the remaining bits? No, we've already designed it. All we do is we make another full adder to generate a sum from the addition of A and B and create a carry into the next column. All right. And if we wanted to have 4-bit adder, we add another full adder. And if we wanted to have a 8-bit adder, we'd have 1 half adder and 7 full adders. And if we wanted a 32-bit adder, we'd have 1 half adder and 31 full adders. There is a problem though, and the problem is this. Whenever you add something with this, and remember we're talking about our sum of products expressions being just 2 layers of logic. For a 2-layer logic, we have a sum of products expression. You have a propagation delay through the AND gates, and then a propagation delay through the OR gates. Well, that takes us through the first circuit here, but we generate a signal which is used as an input to the next circuit. That signal has to propagate through 2 layers of logic to generate an output which is then used in the next level. 2 layers of logic, and what happens is you get this ripple effect. As the carries are generated, their effect is rippled on up. Now, if you look at this guy right here, this addition right here, a carry is generated here. I can't compute this value until the result of this carry is felt. So, for example, if I had just gone ahead and added those 2 bits together without knowing what the carry was from the previous column, I would have had the wrong answer there. I would have had a 1, and there would have been no carry here. Adding and so forth. So each one of these bits, all of those bits would have been wrong because the carries hadn't made their way yet through all of the values. This is called a ripple carry adder. Now, a little bit larger circuit usually sits on top of this in our microprocessors, and that is called a carry lookahead. And an adder based on a carry lookahead circuit. The carry lookahead circuit sits on top of there. And the adder based on the carry lookahead circuit is called a carry lookahead adder. Now, what it does is it takes the A's and the B's from all of the A's and B's. So all of those bits and all of those bits, puts them into one big circuit. And so in this case, we would have had, 16 bits? That's a truth table 65,536 rows long. That's a big truth table to do a Karnaugh map for. But through this logical progression and figuring out exactly how carries are going to be generated for each one of these guys, you can actually generate a single sum of products expression that is going to create a carry look ahead. So all the carries will be computed one fell swoop. They'll all be ready so we don't have to wait for it to ripple through. And there you go. We've designed an adder using Karnaugh Maps and a little bit of understanding of how the addition process works.